You are 3 hours into an oceanic flight, far beyond radar coverage, and with no landmarks below, when an engine fails. You have to make a decision. Do you turn back, or do you push forward? When modern GPS fails, pilots rely on dead reckoning. This is a method of estimating your current and future position by applying a known ground speed and heading to a previously confirmed fix, accounting for the aircraft's motion within a moving body of air. We map these forces using the triangle of velocities. It consists of 3 sides: the air vector, which represents where the nose is pointing and the speed through the air, the wind vector, showing the speed and direction of the air mass, and the ground vector, which is the actual path and speed over the Earth's surface. Looking at the angles within this triangle, we have to separate the result from the correction. Drift is the physical angular difference caused by the wind pushing you off your heading. The wind correction angle is the specific angle you steer into that wind to stay on your intended track. Because the aircraft is suspended in moving air, your airspeed does not match your ground speed. The ground speed is the final resultant vector. A headwind shortens this vector, while a tailwind lengthens it. These 3 vectors form the geometric foundation for navigating without external references. By solving this triangle, we can begin to calculate the exact physical boundaries of the flight. This diagram shows a route from point A to point B. That marker in the middle is the point of equal time, or PET. It represents the geographic point on your route where continuing onward takes the same amount of time as turning back. To find the distance to the PET, you multiply the total distance by your return ground speed and divide that by the sum of your outbound and return ground speeds. Introducing wind shifts this balance. If you are flying into an outbound headwind, your return trip will have a tailwind and be much faster. Because you can cover ground more quickly on the way back, the PET moves closer to your destination. Let's plug in real numbers. You are flying from Mumbai to Delhi, a distance of 600 nautical miles, with a true airspeed of 240 knots. With a 40-knot outbound headwind, your outbound ground speed is 200 knots, and your return speed is 280. Using the formula, the PET is 350 nautical miles from Mumbai. The DGCA exam often tests this using an engine failure scenario. In these cases, you must calculate your outbound and home ground speeds using the reduced engine-out true airspeed, rather than your normal cruise speed. The point of equal time identifies the fastest path to a runway during time-critical emergencies, like a cabin depressurization, regardless of the fuel remaining in the tanks. While the PET is a balance of minutes, the point of safe return, or PSR, tracks your fuel limits. Look at these 2 formulas side by side. The structure is nearly identical, but the focus shifts from total distance to safe fuel endurance. Unlike the PET, any wind component acts as a penalty here. Whether you have a headwind or a tailwind outbound, the effective wind reduces the distance to the PSR. You will always achieve your maximum geographic range in still air. A common trap on the exam is providing the total fuel on board. To find the safe endurance required for the formula, you must first subtract the mandatory 45-minute regulatory reserve from that total time. Try this calculation. You have 5 hours of total fuel, a 45-minute reserve, 240 knots true airspeed, and a 40-knot outbound headwind. Pause the video now and find the time to the PSR. First, subtracting the 45-minute reserve from your 5 hours of total fuel gives you 4.25 hours of safe endurance. When applied to the formula, the result is a PSR time of 2.479 hours. While the PET helps you find the nearest runway in an emergency, the PSR defines the absolute physical boundary of your aircraft's fuel endurance. Let's review the rules. Drift is the result of the wind pushing the aircraft. The wind correction angle is the pilot's proactive fix. PET uses distance in the numerator because it's a geographic halfway point. PSR uses endurance because it's a calculation of your remaining fuel time. Outbound headwinds push the PET forward. Any wind shrinks the PSR distance. And always remember to subtract your regulatory reserves before you begin your endurance calculation. In the cockpit, you'll solve these vector triangles without a digital calculator. Mastering the mechanical E6B or CRP5 is the final step in translating these formulas into a flight plan. Visit Cloud Deck now and take the Dead Reckoning quiz. Cement these formulas today so the examiner cannot trap you tomorrow.